Unit 3, Lesson 7, Linear and Quadratic Systems. So today's lesson is all about finding the intersection between a quadratic and a linear relation. Okay, and in the past, we've always looked at the intersection of linear relations, right? And we've used substitution and elimination. When you're solving a system that's between a quadratic and a linear relation, we can't use elimination because we have an x squared term and an x term. We run into problems combining like terms because x squared and x are not like terms. So to solve a system between a quadratic and a linear relation, you're going to use substitution. And substitution is pretty easy. Because we're working with function notation, our f at x is always going to be isolated for, so there's never going to be any rearranging prior to starting substitution. So it's going to be quicker than what you would have done in grade 10. Okay, so let's solve all these systems of equations. So the steps for solving a system of equations is set your f at x equal to g at x, or the two equations in the system, set them equal to each other. Then combine like terms. Then you're going to factor to find your x values. And then you're going to plug those x values into the original equation to find the y value of the intersection points. And then combine the x and y values and you have your points or point of intersection. Okay, so let's find the solution between g at x and f at x. So the first thing we want to do is set g at x equal to f at x. So g at x is x squared plus 10x minus 6, and f at x is 8x plus 9. Now let's collect and combine our like terms. So I'm going to bring all my terms to the left side of the equal sign, and now I'm going to combine my like terms. Okay, now I'm going to go ahead and factor to find my values of x. So I need two numbers whose product is negative 15 and whose sum is 2. So your two numbers are going to be negative 3 and 5. And because a is 1, those are our factors. So let's find our x values. So our first x value is going to be at 3, and our second x value is going to equal negative 5. So remember, the end goal is to find the intersection points. So what we just found are the two x coordinates in each of our intersection points. Now we need to find the y coordinates to go with those x coordinates so that we have our full point. So to do that, I'm going to take each of those x values, plug them back into one of the two original equations to find what the y value is. And it's smart to plug it back into the linear equation because that's easier to work with, right? When you plug a value into that linear equation, it's going to be a couple quick steps to solve. Rather than plugging it into the quadratic, it would be a little more work to plug it in here. Okay, so I'm going to take my original equation and let's plug in each of our x values. So first, let's plug in 3. And then second, let's plug in negative 5. And now let's do the math. Okay, so therefore, the first point of intersection between f at x and g at x is at 3 and 33, and the second point of intersection is at negative 5 and negative 31. Okay, let's do the same for part B. Let's solve this system of equations. So first we need to set f at x equal to g at x. Then let's collect and combine like terms. So I'm going to bring all the terms to the left side of the equal sign. Now I need to ask myself what two numbers have a product of 2 and a sum of 1. And you're going to realize that there are no two numbers that do that. So this is not factorable. If you were to try the quadratic formula, you would come up with the same result. You would plug in all your values into the quadratic formula, and then you would get a negative number underneath the square root sign, which would mean, again, not factorable. So just to be sure as a check, we could also use our discriminant. Remember, b squared minus 4ac tells you how many solutions the system has. So let's go ahead and plug in our values into the discriminant and see if it indeed also concludes that there are no solutions. So we get a negative value. So when the discriminant is less than 0, that means no solutions. So I just stuck this question in here to show you that it's okay if you come across a problem where, the factoring doesn't work, quadratic formula does not work, okay? It just means that there's no solutions. We did learn about that, so you are prepared to handle situations like this. So I want to show you what I mean by a system that would have 2 points of intersection, a system that has 1, and a system that does not have any points of intersection. So for example, if we have a parabola like this, okay, and we have a system that involves a quadratic and a linear relation, a system that would have 2 points of intersection would look like this, right? Because there's a point of intersection there and a point of intersection there. So there's an example of where there are 2 points of intersection. Okay, a situation where there is only 1 point of intersection would be when they intersect at the vertex of the quadratic. Okay, so in this situation, that is the only point of intersection. And finally, an example where there would be no points of intersection could be like this. If you have the quadratic and then the linear relation is somewhere down here, those two relations will never intersect. That's like example B that we solved above. Determine the number of points of intersection. So we don't need to find the intersection points, we just need to figure out how many there are. So for this, let's go ahead and set g at x equal to f at x. We'll solve that and then use the discriminant to figure out the number of points of intersection. Okay, let's collect and then combine our like terms. Okay, so now let's use our discriminant to figure out how many solutions we have. So because we got a value greater than 0, we know that there are going to be 2 points of intersection. Okay, so as soon as that discriminant is greater than 0, it means there's going to be 2 points of intersection. Let's try this one. So we'll set g at x equal to f at x. We'll solve this. Now let's use our discriminant to find out how many solutions there's going to be. So because our discriminant was equal to 0, that means there are no points of intersection. Okay, let's finish with an application problem. Justin is skeet shooting. The height of the skeet is modeled by the function h at t is equal to negative 5t squared plus 32t plus 2, where h is the height in meters, t is the time in seconds after the skeet is released. The path of Justin's bullet is modeled by the function g at t is equal to 31.5t plus 1, with the same units. How long will it take the bullet to hit the skeet? How high off the ground will the skeet be when it is hit? So skeet shooting is essentially somebody fires off a piece of clay, okay, from the ground, so it's going to follow this pattern, goes up in the air and then it comes down. And then you have a shooter over here with a firearm and they're going to shoot that clay in the air. So the path of the bullet from the firearm is your linear relation. Okay? So this is essentially just, again, solve a system that involves a quadratic and a linear relation. So let's go ahead and set h at t equal to g at t. Let's collect and combine our like terms. Okay, so since we actually want to know when the two lines cross, we need to solve this for t, so we need to factor it. Okay, so let's use our quadratic formula. Okay, so we're going to have two solutions. The first solution is what I've written down there. And the second solution is going to be the answer to that equation. Okay, so go ahead and solve that, and you get the first t value at negative 0.4 and the second t value at 0.5. Right away we can reject our first t value because we can't have negative time, right? So we know that is not going to be an intersection point that we are concerned with in this application question. So we can conclude that the bullet hits the clay skeet after 0.5 seconds. Okay, but there was still another part of the question. It says, how high off the ground will the clay skeet be when it is hit? Okay, so we know that it's hit at 0.5 seconds. We need to now figure out how high that is at that time. So we're going to take time of 0.5 seconds, plug it into our original equation, and see what the height is. So I'm going to choose to plug it into g at t, the linear relation, because the linear relation is much easier to solve. Okay, so let's plug in our time of 0.5. And then let's solve that. So that means at 0.5 seconds, the bullet hits the skeet, which is 16.75 meters above the ground.